Good morning and welcome everyone. Thank you for joining the Kootenay Conservation Program's Winter Webinar Series. This year our series focuses on the theme of From Alpine to Valley Bottom, Conserving Essential Habitats in the Kootenays. My name is Marcy Marr and I am KCP's Stewardship Coordinator and will be the host for today's webinar. Nicole Trigg, KCP's Communications Coordinator, is also on board to ensure that our technology runs smoothly this morning. Given the rich heritage of stewardship in the Kootenay region, I'd like to acknowledge that KCP's work occurs in the traditional territories of the Ktunaxa, Shuswap, Sinixt, and Syilx peoples, who've lived here and stewarded the land and water for many generations. While some people are still joining us, I'd like to talk a bit about the Kootenay Conservation Program, known as KCP. We are a broad partnership founded in 2002 and currently comprised of more than 80 land and water conservation and stewardship groups, government agencies, resource industries, and agricultural producers. KCP's mandate is to coordinate and facilitate conservation efforts on private land and to generate the support and resources necessary to maintain this effort. We achieve this through increasing the effectiveness, collaboration, and coordination of private land management and stewardship activities, building financial and technical capacity of our partner organizations, and serving as a network to achieve efficiencies, synergies, and ultimately greater effectiveness. So far, we have over 60 people on the call today, and so we're always interested in knowing who's joined us. So please respond to these two questions in the chat box, which is at the bottom of your screen. Let us know where you are based and your affiliation, please. I'll give you a moment to do that. And if you've just joined us, I've asked people to put where you are based and your affiliation into the chat box, please, so we can see who all is on the webinar today. Okay, great. So today is our fourth and final webinar in our four-part series. And we've had such an excellent and interesting group of speakers this year. If you've missed our webinars, Drones and Dens, or BC's Old Growth Forest, or Creston Valley Green Mapping, you can find links to the recordings on KCP's website, kootenayconservation.ca. So I'd like to tell you a bit about our webinar. It'll be approximately 40 minutes with up to 15 minutes for questions at the end. As an audience member, you're on mute for this presentation. If you're not familiar with Zoom, who isn't these days, but just in case, make sure you've located your control panel at the bottom of your screen. And if you have questions for Ryan about the presentation, please use the Q&A option and enter your questions in there, and they'll be answered at the end of the presentation. If you're experiencing any technical issues or need to be in communication with Nicole Trigg about some concerns or issues, please use the chat option. So Q&A, that's where your questions go for Ryan about his presentation, and the chat option is where any comments or questions for Nicole. Thank you. This webinar will be recorded and it will be made available on our website in a follow-up email that we send you along with the presenter's contact information and a short post-webinar survey. It takes a few minutes to fill out, and we really appreciate your feedback. It helps us plan for next year's webinar series. And we're always grateful to our funders and supporters of KCP, without whom we couldn't do these types of programs. So I'd now like to introduce today's speaker, Ryan Durand, who's an ecologist and project manager with EcoLogic Consultants. Ryan has a Master's of Science from Edinburgh Napier University and is a registered professional biologist. He has spent the past 20 years working throughout Western Canada and the Arctic on a wide range of ecosystem mapping and inventorying projects with a focus on wetlands and at-risk species. In today's presentation, Columbia Valley Wetland Mapping Project, combining digital technologies in wetland ecology. Ryan will present an overview of this ecosystem mapping project to help manage the 180-kilometer-long Columbia Wetlands, describe how combining digital imagery, LiDAR, and drone technology can be used to map and classify wetland types according to the provincial Biogeoclimatic Ecosystem Classifications, and provide examples for how this classification can inform future conservation efforts. So thank you, Ryan, for being a part of KCP's webinar series, and I'll turn it over to you.
Thank you, Marcy. As Marcy said, my name is Ryan Durand. I'm a biologist with EcoLogic Consulting, and I have been working for the last year and a half or so for the Columbia Wetlands Stewardship Partners, doing a ecosystem mapping project for the entire Columbia Valley Wetlands. So just a little overview of the presentation here. I'm going to talk about the study area for people who are not familiar with this area, get into the mapping methodology, field verification, and what the final product is starting to look like, and then what's next. So what can really be done with all this data after it's been created. And I apologize, my voice is a little harsh today. So the study area is quite simply pretty daunting. It extends all the way from Canal Flats in the south up to Donald, which is north of Golden. Roughly 180-kilometer long valley, I believe. It's the headwaters of the Columbia River, of course, starting just at Canal Flats. And it's approximately 23,000 hectares of wetland and floodplain valley bottom systems. This mapping project only focused on the valley bottom and did not extend up into the hillsides at all. So a little overview of the different main features of the study area, I guess, starting from the south and the headwaters. The interesting thing with this is that because it's a headwater of a major river, is that the changes considerably as you go along this valley bottom. So even though it's one big connected wetland system, the vegetation and the ecosystem communities change significantly as you go. So starting from Canal Flats in the south, getting up into the southern end, I guess, still of the thing, is Fairmont Hot Springs. You can see it's big, wide open valley bottom, mostly formed, or totally formed in most cases, by the Columbia River floodplain, mostly bordered by quite steep and erodible lacustrine sediments and fluvial sediments on the sides. And as you look at these couple photos, the main thing that you'll see is that there's very little development in the bottom. That's what makes these wetlands so amazing and so important, is that they are really undeveloped for the most part, except for little bits here and there, and of course the railway along one side. So while that makes these wetlands amazing and quite intact, it also makes it quite difficult to access any of it and actually do any mapping and field verification. This is a picture up in Parsons, getting up into the northern end. And then finally all the way to Golden, just past Golden. So the entire area is this amazing complex of these ever-changing fluvial system of channels and floodplains and levees and wetlands, all constrained by the rather steep valley. So for a quick overview of the mapping methodology, this was largely done on GIS, of course. The intent was to try to classify all of the ecosystem types to the provincial Biogeoclimatic Ecosystem Classification system. So that is the province-wide system that describes all of the ecosystems in the province based on location, based on climate, based on parent materials, and based on vegetation. Normally when we're doing these kind of ecosystem mapping projects, we start with a terrain mapping exercise where a professional geoscientist will go through a stereo imagery and actually map and describe all the different types of parent material. So colluvium, glacial till, lacustrine sediments, fluvial sediments, and then also depth of those sediments, their superficial expression aspect, slope, all the different qualifiers that really influence vegetation and ecosystem development on it. Traditionally, in most of these ecosystem mapping projects, wetlands are largely glossed over. You put a little polygon around it and say it's organic soil and move on. So most of the time they end up being just kind of these generic blobs, if you will, of everything wet lumped into one big polygon, and the ecosystem mapper might come through and separate it a little bit, but definitely on the terrain side, they're quite lumped together. So when you're trying to map a large fluvial system that is quite flat, with little relief within it, and it's largely all one type of parent material, it's all fluvial material, the traditional terrain mapping approach doesn't really work. So we use a modified terrain approach that we're going to talk a little bit with LiDAR. And then on top of the LiDAR, the first step is to do the terrain mapping on the LiDAR. So you're looking at all the relief, all the little changes you can see in the topography. And then from that, we will use ortho photos in this case. We didn't have access to stereo photos to do our ecosystem mapping. Once you have a draft mapping of your entire study area, next step is to get out into the field and do the actual field verification to actually confirm what you think you see on the air photos in the actual field. And then from there, you can produce a final map and then move on to the fun stuff, all the interpretation. So LiDAR has been around for quite a while, but it's still, I don't think, used as widely as it could be, especially for ecosystem mapping. And LiDAR in its essence is really just a plane, a helicopter, or even a drone these days, flown over a site, laser machine, I don't know how to describe exactly, a laser on it that shoots back down to the earth, and it essentially measures the time of the response of the laser hitting the ground, bouncing back up. Then it can use that to map in very detailed, sometimes centimeter accuracy, of the elevation of what's down there. It penetrates through all the vegetation, buildings, and everything except for water, and it can actually measure height, and you can classify it by layers. You can do a bare earth layer, you can do a tree layer, you can do a vegetation layer, you can do whatever you'd like. So this is just an example of just the scatter of a raw LiDAR data set with just elevation, and just kind of gives you an idea that where it hits water, it records nothing and shows the vegetation. You can classify LiDAR using height if you want. So this is a classified one showing the different layers of vegetation, where that dark red is your tallest trees, the orange is your middle layer, and then down to that light green, the blue is like your more herbaceous and low layer. So you can actually use it to show tree height and vegetation height, help classify vegetation if you're interested. You can also use it to do all kinds of 3D modeling. This stuff is incredibly computer intensive, so it's not really practical from a mapping perspective per se to look at it across a large landscape, but you can clue in on little areas and look at differences in tree heights. For instance, in this little 3D profile here, you can see some of the larger trees down on the bottom. So if you were doing a mapping exercise and you didn't have very good imagery, or if you had good imagery and you wanted to pick out the oldest trees, the tallest trees, etc., you could actually use this kind of a classification system to describe them. What people are more familiar with, and the product that we are using for this project, is more the hillshade. So this is the bare earth derived LiDAR, and is just showing the elevation. It's a modeled product from the raw LiDAR, just showing the relief, and really shows the example of different types of topography and parent material in the Columbia Valley. You can see all those, the flat area in the bottom, which is basically the big, huge fluvial system. You can see those really eroded banks on the sides. You get into that softer old lacustrine, the old lake sediments that's eroded on the sides. And then when you get farther up off the valley into the mountains, you can start to see the rock and the tills and everything else. So the general process that we were using here is we had a wide variety of products with the size of a study area and budgets and funding available. We didn't have the luxury of being able to fly the entire valley and have perfect imagery and data for everything. It's pretty typical for most of our mapping projects. We don't have that luxury. So we had to use a combination of different sources and different products and different qualities and even probably even more importantly, different dates of imagery. So if you have a ortho imagery, this is one part of the valley. This is what the exact same area looks like using the LiDAR. This is where I'm saying you can start to do your terrain mapping of the system using this. So using the LiDAR first before you even start looking at the imagery allows you to just really identify, in this case, the river obviously going through it, areas of active flooding that are really modified every year by flooding. You can sort of see the little bits of levees, the elevated areas around the outside of the channels. And then you get back in behind the levees where you actually see the flatter areas, which is more standing, permanent or flooded water, everything in between. So from a mapping perspective, when I use that combination of this LiDAR and my ortho imagery, I can go through in relatively good detail and start describing all these different types. So our normal process is that you would take the LiDAR and you would do your terrain features first. So you'd map out the elevational difference, textures, all those differences first. And then you overlay that on top of a ortho image and then divide up all those polygons again into the vegetation types. So the yellow boundaries you can see are drawn around, again, the river floodplains, the treed floodplains, cottonwood floodplains on the sides, and a variety of marshes and swamps and other systems within it. You also start to notice in some of this imagery, those areas that are completely underwater when this was taken. And especially in the Columbia Valley, this is more of a problem than usual for mapping because the floodwaters are of a very high silt load. So everything kind of gets this white, washed out look on the imagery, which makes it really hard to interpret anything. So to overcome that issue of the image quality and also the access issues or limitations of access, as much as I would love to have canoed the entire river all summer, it just wasn't possible with the time that we had. We started to look at some alternative methods of how to do some verification of this area. So typically on an ecosystem project, we would be driving, using a helicopter, boat, etc., to get into our sites, and then you'd be on foot and doing transects through areas and actually doing a full plots and there's some types of sampling plots to describe and classify all the ecosystem types. So that was still done in this project initially where we were able to get down, but really it was quite limited to bridges and the odd access where it hit crown land. A lot of the access points are actually private property, so it made them more difficult to access it. So we had limited ability to really get into large stretches of the study area on foot and actually properly sample it. So to expand on the amount of ground we could cover, we used drones, which is the fun technology that everybody's using these days. And they're amazingly adaptable and amazingly simple to use, really, and actually not even that expensive. So again, to give you the idea of the total study area, it's a large area. All those little blue dots on there are my drone flight paths. So the wonderful thing about most of these drones is every time it takes a photo in the air, it will actually tag it with GPS coordinates. They're not always super accurate. They're normally in the 5 to 10 meter kind of range, but for doing this kind of project, that's perfectly good. So the whole process is that every time we could find an area where we could legally fly and find a safe place to fly, we would get in and fly a couple kilometers of the area, take hundreds and eventually thousands of photos throughout this valley and also video, and try to cover all the areas where we could not access on foot. And as I said, most of these images come up with a georeference tag on them. So from there, it's simple to take it and import it into the GIS and plot the actual photo location. A little close up of where they are. So in this area, you can see on the right-hand side there, the dark blue, the flight lines. And then on the lower left, you can see the more individual actual photo centers as I flew randomly around looking at different parts. So once you have that all loaded into the GIS, as I'm going back through in the office after the field season and starting to turn my draft ecosystem map into the final ecosystem map, instead of just relying on the small percentage of the 9,000 mapped polygons that we actually could access on foot or see from the edge of the road to try to describe and classify them, I all of a sudden have thousands of points throughout the entire study area of drone imagery. So in the GIS, as you're mapping along, you can literally just click on any one of these little points and it'll bring up a hyperlink to the actual photo that was taken from there. If you get right into it, you can set it up so it tells you the direction the photo was taken, elevation, and everything else. But the whole idea is you could just do these flight paths all through the area and just get a better idea of what's actually there. So you can get an idea of the complexity of the system in here, and quite a lot of it's quite fine. The floodplain areas where there's actually the trees and the shrubs are normally pretty distinct. The channels are too as well. But as soon as you get into the backwater areas where there are various types of marshes and shallow open water communities, they get much harder to interpret on an air photo and on the LiDAR. And as I was mentioning before, and lots of the imagery would look like this. So the LiDAR would still show up a lot of what's underneath these flooded areas. But when you get onto the air photo interpretation, try to classify any of these, it's incredibly difficult to figure out what's there. So by supplementing this kind of imagery with a whole bunch of drone flights over top of it, instead of looking at this air photo and all these murky flooded areas and trying to interpret what may be there based on its elevation, its location, the water movement, and whatever bits of vegetation you can see, instead you can go to every one of those photos, instantly pull up an image of it, and then it makes it much easier to interpret what's there. So the whole drone application, this isn't anything particularly difficult or technologically advanced. It's really just incorporating a relatively simple process into what we're already doing and being able to cover a much larger area. One of the most challenging aspects of most of our larger mapping projects really is access and be able to ground truth enough of our mapped areas to have confidence in our final product. Mapping is normally only as good as your actual data from the field is, because you obviously can't field truth every single polygon in a project. There's just not simply time or budget to do it. So you have to do a lot of using professional judgment on interpret an area where you have data from to figure what the ecosystem type is and move over to the adjacent areas that you have no data from and apply those same classifications to it. So by using the drones as we go, we can really expand the amount of area we can cover. So once we are back in the office and we have all this great field data and all these drone photos, there's a very labor intensive thing to go back through all the mapping and start classifying it. So the final product from this project really is GIS data. We have a very large map of the entire valley. As I was saying, there's somewhere around 8,000 or 9,000 polygons of mapped ecosystems in it. Most of it is mapped at a relatively fine scale of about 1 to 1,000, 1 to 2,000. So we're really trying to make them as pure of communities as possible. And the benefit of all this is you have, I guess for the first time, first of all, you have a base layer of everything that actually occurs within that wetlands. To date, this is one of the first attempts to ever try to map at all. So before now, we really had no idea of what percentage of different wetland types, for instance, occurred within the wetland. So now we can pull out statistics and hectares of the different wetlands. So we can calculate the amount of floodplain forests, of different marsh communities, of different swamp communities. We also can do all sorts of additional mapping and modeling with that and use it to describe rare ecosystems, for instance, habitat, really wherever you want to go with it. To give you a little bit of a snapshot of what that looks like in the larger area, this is a portion of the final ecosystem map using just what we call the first decile ecosystem classification. So in each one of those little colored polygons there could be up to 3 different wetland or floodplain types mapped within there. This is just portraying the dominant one or the most common one within it. So right away you can see the application in this, that you can start to build maps of the entire watershed and describe where the rare ecosystems are. We have people like Rachel Darville using this data right now to start working on biodiversity hotspots. So she can take this kind of data, overlay her bird data and her rare occurrence data, and start modeling where other habitat that meets that same criteria is in the valley, and try to one, make target areas for her to go do more ground truthing and surveys, or just really get a better idea of the habitat potential across the entire valley. So the what's next part is the really exciting part of this, and I don't have more slides to describe what's next because it hasn't been done yet. The main thing, as always in a project like this, is we hope to do more inventory and classification to improve the mapping. There's definitely a lot more fine scale ecosystem classification that we can done throughout the valley. We had limited field time, as I said, to actually sample the ecosystem types. So some of them are mapped across the entire landscape where there's probably a lot more fine-tuned gradients, especially in a lot of the swamp communities. This floodplain system is quite challenging because in some years everything floods. So trying to decide what is what we call a low bent floodplain, so like a shrub dominated floodplain system that either scours or has a depositional environment basically every year, dominated by your normal willows and alders. Trying to decide if it's that versus one of the various types of shrub swamp communities that occurs normally in a more protected environment where it may have some flooding throughout the year, but it generally doesn't have any scouring or deposition. So getting out into the field more and trying to really nail that down will be a huge benefit to improve the quality of this overall. The other big thing to realize, as I talked about a little bit, is that this is really just the first initial base layer. Like once you have this comprehensive layer of the entire valley, then you can really start doing fun stuff with it. You can start modeling all the ecosystems at risk, and there are lots in there. Most of the cottonwood floodplain systems in this area, they're currently getting revised by the Conservation Data Center to update the status on them, but pretty much all of them are blue listed ecosystems. So one of the future projects that they're talking about is really looking at where the mature and old cottonwood systems are throughout the entire valley, to start looking at how those areas can be protected or maintained. Also looking at those in terms of bat habitat and other species at risk habitat. There's also 3 marsh communities that are blue or red listed throughout there. There's one low bench floodplain ecosystem that occurs quite often throughout the valley. That's actually a red listed one throughout the province. So being able to model these and actually go back in the field and to verify they really are there and get a better sense for how much of that's throughout a landscape can be incredibly powerful when we're talking about conservation, about management, or about arguing to protect a certain area. As I mentioned, there's other people in this project right now that are working on doing SAR modeling. So they're actually using these data to model habitat and find the biodiversity hotspots and feeding that into looking at landscape linkages and where other important areas are. Probably one of the most exciting ones to me, if you can repeat these things in the future, is looking at change over time. So once you have a base layer, you can go forward or backward if you have image availability and try to learn about how these ecosystem types are changing over time. So if we had the ability to go back and look at historical photos that we could georeference and put into this GIS, you could actually go back in time and see what things were before. And likewise in the future, say 5, 10 years, whatever's time frame down the road, if you got new imagery, you could do the same thing. You could revise and remap this product and try to see what is changing over time. Is it dramatic? Is there any change? Is it detectable change? And one of the other projects that we are working on right now with Suzanne Bailey and a hydrologist out of Alberta is doing hydraulic modeling. So they're using remote sensing to try to figure out where permanent water is within the landscape using long-term time series of satellite imagery and modeling to try to decide if there's permanent water within the basins, trying to figure out what areas are getting wetter and what areas are drying out. And more importantly, if there's anything they can do about that. Is it just a climate change related thing? Is it just the river is downgrading and cutting areas off so they don't flood anymore? Where is it coming from? So we are taking that hydraulic modeling and right now trying to combine that with the ecosystem mapping and trying to describe the, I guess, sensitivity of selected subbasins within the watershed to hydraulic change over time. So looking at areas that are isolated from the main stems of the river, looking at all the levees and the breaks in the levees to try to understand how and when water, especially flood water, will come into these levees and saturate them earlier in the year and how much they dry out through the year. This is a landscape that majority of the water inputs to a lot of the wetlands that are cut off from the main channel get all of their water from the fresh air. They don't get a lot of precipitation or inputs throughout the year. So really understanding which ones are protected and which ones are vulnerable to changing water flows over time is really important to figuring out which ones can be protected. And I mean, this is just a snapshot of a few things that could be done with this. There's so many more. And that went way faster than I thought it would go. So Marcy, I'm done early.
Great. Good job, Ryan. That was fabulous. And what a great contribution to have this information available in the Columbia Wetlands. It is such an important landscape for all of us here in the Kootenays. So I have questions are coming in. So if you have questions, please enter them into the Q&A box. That way I'll see them. I'm not looking at the chat box, Nicole is, but if you've got any other technical questions, you can put it in the chat. But please put your questions in the Q&A. And someone had asked whether this recording was going to be available. And yes, we are recording this. It will be available on KCP's website, kootenayconservation.ca. It'll also be in a follow-up email to you. You'll have a link as well as some other materials. So with that, Ryan, here's your first question. So was the drone imagery collected during a specific time window, as in a time of year when the photos would be the most helpful for classification?
Yeah, so they're pretty much all flown during late July and then a few a little bit later in the year. They corresponded with the fieldwork window that we selected and really based on when the twofold, I guess, when the vegetation was green and we could actually identify stuff and when the water had receded enough last year that we could actually get into it and do the field work. So it was late July, early August, I believe. For a lot of the ecosystem work, though, that for the classification part anyway, that the window is quite large because you need the vegetation to be developed enough to identify when you're on the ground. But if you're looking at ecosystem classification, you can tell a marsh, you can look at, for instance, a cattail marsh, a bulrush marsh, a shallow open water community, or a shrub community. You can differentiate that in a much larger period throughout all the summer.
Okay, great. Another participant is interested in your drone photos and said that they were shown sort of at an oblique angle rather than looking straight down on the ground. So could you speak to the advantages or disadvantages of oblique images versus vertical ones?
Sure. Yeah, that was just one that I showed that happened to pop up in that spot that looked nice. When after you fly, like I said, I set the drone normally on a timed interval, so it automatically takes a photo every 2 seconds and then just fly and take a variety of images. I take them straight down, take the oblique, take 90-degree ones. I find that the oblique show you the most detail. When you look straight down, it's not always as useful. So I typically just do the oblique ones. But like every one of these, every time you put the drone up for the 10 or 15 minutes the batteries last for, you normally end up getting 700 to 1,000 photos. So they're at every angle you could imagine. And most of the time when you're flying, you have a heads up display so you can see exactly what the camera is taking a photo of. So you concentrate on areas that are hardest to figure out, avoid the cottonwood and the easy stuff, and try to hit the marshes. Also try to hit them from different angles, from multiple passes from different angles, especially depending on the light level. But yeah, oblique ends up being the most useful for interpretation, I find.
Okay, great. We've got somebody from the Slocan Valley that said, this is so interesting. Ryan, does this compare with the wetland mapping you're doing for the Slocan Valley, the Bonanza Corridor? Are you using similar technique?
Using very similar techniques. The difference up there is that a lot more of that map is terrestrial than aquatic. So we actually have proper terrain mapping that we can use to guide it. But yes, I have LiDAR and stereo imagery, so we can actually do proper air photo interpretation in a soft copy system. So you can see all of the air photos in the terrain in 3D within the imagery. So you can do a lot finer detailed mapping. The product just simply wasn't available for the Columbia Valley. And yes, we're using drones extensively up there to fly everything. They're definitely not as useful in the forested environment though. Like you can imagine getting the drone up and taking oblique photos of a conifer forest, you don't see a lot, versus this wide open wetland valley, you could just see so much.
Yeah, it's extraordinary. So someone's wondering if this data is publicly available or what's its current access?
So that would have to be directed to the Columbia Wetlands Stewardship Partners. It's their product. I imagine or hope that it will be very publicly available when it's all completed.
Okay. Back to drone flights. What do you recommend for timing of drone flights to optimize ecosystem classification, water level, time of year? You might have already answered this, but if you have anything to add.
Yeah, well, I don't do it as a standalone thing normally. So far, how I use it is we decide when our field sampling period is going to be anyway. So this isn't done independently of regular field work. So a typical day would be going out and doing regular ecosystem plots to actually characterize and describe the ecosystem types. And then while you're there, you spend 15 to 20 minutes and fly the drone out a couple kilometers in every direction to get a much larger idea of what's there. Back to the truck, drive to the next site, do more plots, fly the drone again, that kind of idea. So you're combining both of them. So typically it's done at the exact same time as when you would want to be there to do vegetation plots anyway.
You're out there in the Columbia Wetlands?
Sorry, what was that?
Sorry, my internet's breaking up. You had said something about the end of July or early August when you were out in the Columbia Wetlands this past summer. Is that right? Is that the window that you found was best for the vegetation and the water levels and all that?
Yeah, well, the vegetation, especially for wetlands, is always going to be better July and August, especially when the sedges and the willows are easier to identify. But for the Columbia Valley, it's really dependent every year on what the water levels are like. This year was a bit later, or last year was a bit later than usual, I believe. But typically July and August is the ideal areas.
Okay, someone says, thank you very much for a great presentation. Can you expand on more examples about the use of this technology to assess climate risk, ecosystem risk, and how this would support ecosystem adaptation strategies? Thanks.
I guess that's more an interpretation side of it and a longer term thing. This is very much just some additional technologies that can be used to support a more classic ecosystem mapping product. But once, as I was trying to say, once you have the base layers set out, that's when you can start doing an interpretation and studies. I don't know that it could be directly used in any way to support a climate change study. That's where you would need to repeat studies over time to look at change over time, whether that's backcasting and historic photos or current ones. And that's also where Suzanne and Ryan McDonald are looking at the hydrology, using gauges, looking at longer term data, looking at modeling to try to predict and figure out what variable climate change scenarios are going to do to the wetland types in there. And that's mainly about water flow, water timing, and water permanence. So it's not a system to specifically address any climate change adaptation or assessments, rather as one more tool, one more bit of data in the puzzle that somebody else gets to put together.
Are there plans to submit this mapping to be loaded into the provincial terrestrial ecosystem mapping warehouse and the BCGW?
I would think so. I think we have to decide if we want to do more field truthing of it next year or not. But yeah, the idea would be that this is a publicly available document, and yeah, submitting to the province would be ideal. Like I said, I've already been approached by the CDC. There's individuals working on updating some of the conservation status right now for the FMO2 cottonwood floodplain system that we found pretty extensively throughout the Columbia Valley. But because we are somewhat limited in the amount of field time on this, some assumptions were made on where these ecosystems occurred throughout the larger area. So I think if we want to get it to the state where we really want to have it as a provincial layer, you probably have to do a bit more field work to fine tune some parts.
Okay. And how far away from the wetland was the data collected? How much adjacent uplands are included in the mapping, to include more of the Columbia Valley or Columbia Wetlands Wildlife Management Area?
Very little. So it pretty much went to the edge of the flood area. It really did not go up into terrestrial environments at all, except for little bits here and there and some islands and stuff. And this method was really, like I was saying, it was using the LiDAR, and it's using digital orthophotos. So it's all two-dimensional material for the most part. If you want to get up into the slopes, into the forests and those communities, you really need to do proper terrain and proper stereo ecosystem mapping, because you just can't accurately map in, especially forested communities, without having stereo imagery to see what's really there. If you're just doing that on a two-dimensional orthophoto, you really can't properly classify a lot of the ecosystem types in my mind.
Okay, here's a two-part question. If you were to send people in boats to ground truth to add value to this data set, what would be your first priority?
That'd be awesome. So I've actually talked with Neil Fletcher a fair bit about this in the last little while.
This is from Neil.
Okay, that's great. I don't think I'd have a particular priority. We could look at the existing data and see where the field plots were and see where the holes are within that. But wetlands in particular, or in the Columbia Valley, wetlands in particular, except for some of the shrub communities, the classification of most of it is actually pretty straightforward. So it would not be a overly difficult exercise, I don't think, to have people bomb through large areas and do relatively simple plots with a lot of photos and GPS points to describe what's there. That could be very useful to try to better classify and map some areas. Like for instance, a cattail wetland. You can regularly see them on their air photos, but when you get into some of the older imagery, some of the bad imagery, it gets harder to decide if that's what they are. Whereas anybody in the field could take a photo of them and put that point on the map and very instantly have a data point that'd be really useful to improve the classification.
Okay, here's the second part of Neil's question. So would you or could you consider using machine learning to train and find ecosystems at risk with the data you've collected, or would you stick with visual interpretation going forward?
I see by machine learning, it's mostly talking about more remote sensing kind of predictive stuff. Those systems work great if you have the luxury of having nice, consistent, high quality imagery data to begin with. I find that as soon as you have variable products or not the best resolution, or you have to mix different imagery from different dates and different sources together, that the predictive modeling becomes much more different. Because really, to do any kind of predictive mapping with machines, you have to have what's known as training data. So you have to have a spatial point saying this color, this texture is this community type. and those have to be consistent and repeatable across a landscape. So as soon as you have different imagery products, you have to either all of a sudden repeat your training sites, in my mind, so you can show the difference, or you have to make a lot of assumptions to how to try to combine it together. So I find that remote sensing for ecosystems is quite effective on large landscapes where you don't need really fine resolution. It's also really good on large landscape where you have really easily definable rules about slope, elevation, mostly, and color, so you can easily classify stuff. But when you get into wetlands, when you can have multiple communities that are basically all in the same water gradients in the same landscape position, and often even share quite a few of the same vegetation types, it gets much harder to do any kind of automated process to figure out what's there. That's not to say that manual airfoil interpretation is more robust, because it has a lot of bias from the observer and the mapper within it, but I don't know if the ecosystem classification rules are really there yet to automate it anymore.
Okay, next question. So were there any surprises or major differences in your interpretation once you had ground truthed the remote imagery?
Absolutely, there always is. Like, that's one of the fun parts, right? You have a big project and you have limited knowledge of what's there, and you map it all out and try to figure out what's there. And as soon as you get into the field, a quarter or half of what you thought was there is just plain wrong. So our rule of thumb is always that when you're doing ecosystem mapping on your draft one anyway, it really doesn't matter if you're right or wrong with the classification. It only really matters that you're consistent. So if you're calling a marsh a WMO1 watershed, beach sedge marsh, if you're calling whatever ecosystem type that, as long as you're consistent in how you map that across a map, it's very easy after you've done field truthing to go back and revise it and update it. If you're inconsistent and your classifications are random and all over the place, it's incredibly hard to do any updates.
Yeah. Okay. If you wanted to see changes over time, now that you have the baseline mapping, do you need to take a full range of photo techniques, or can you rely on drone imagery only, or some combination?
I guess it would depend on scale. So if you have a small steady area, you could probably get away with doing some drones or doing field plots. If you want to do the entire wetland again, you would probably need new aerial imagery obtained for the entire area. That would be the ideal. But even if you're doing updates and change over time, you can't just have one thing. You need some kind of an imagery, you need some kind of field data to verify it, to see what's actually changed.
Okay.
Those are great, but they're kind of limited in range and how much you can cover. Like on a typical day, between having enough batteries and charging batteries continually, if you're just flying the drone all day long, you might be able to do 10 or 12 flights. So each one might cover a kilometer or two. So you're really limited in how much you can cover. And that's just doing random photos. If you want to actually fly the drone, make ortho imagery, so do like an actual proper nice ortho map of an area, then it's even more time consuming. When we do that, it normally takes a couple hours to do maybe 100 hectares with a drone. So they're a great tool for reconnaissance. They're much slower for actually making aerial imagery in a larger area.
Okay. So with your experience, can you estimate how long it might take to map a specific size area, or provide finalized layers or maps? And this is from Mark Andre, so maybe he's got Creston Valley envy. Well,
it's totally dependent on the size, of course, dependent on what kind of a scale you would like things mapped at. For instance, in this one, we tried to map it quite fine. So there's a very large difference in the amount of time required if you're looking at a 1 to 1,000 scale map versus, say, a 1 to 20,000 scale map. It depends on what kind of classification and final product you want to get out of it. So the short answer is there's no one simple number or time thing that you can put on it. It's really a per project thing. And they're often a lot of work.
Mm-hmm. So is this transferable to get to what maybe Marc-Andre was looking for? If what you've done is transferable to say the Creston Valley, that you've, have some things you've tested out at the huge Columbia Valley, hopefully that would make it easier if you were then to go to Creston.
Yeah, totally. I mean, this is transferable to any ecosystem project for the most part, right? Like this is parts of this is what we do on mapping anywhere in the country. It's not particularly revolutionary. It's just adding one more tool into the system to kind of expand what you can do in the field, I guess. And especially in an area where access is much more challenging than usual. So yeah, lessons learned for sure. There's all kinds of stuff you can use from this. Is it going to change or reduce the amount of time it takes to map a given area? Probably not much. It's more just an extra thing you can do while you're doing it to have a better result, I think. So typically when we do a large ecosystem mapping project, you're budgeting number of days based on number of plots you think you can do with your access. If you're lucky enough to have a helicopter or something, it makes it a lot better. But you're often aiming for only being able to actually field truth. If you're on a good project, like 20% of the polygons or 20% of the area that you map, you're lucky if you can get in there and sample that many times. So if you're able to do that level of sampling, plus have a drone up in the air while you're there doing these visual observations in a much larger area, you're really just increasing the accuracy of the overall map, but you're not necessarily reducing or saving time.
Yeah, okay. Do you see the provincial LiDAR data becoming more readily available for conservation use in the near future?
Well, we talked to them last year, a data sharing agreement to get some of this LiDAR for this project. They said that this year it was going to be freely available online. I have not heard an update on it. It's mentioned quite often and I hope it's available at some point. I can't speak for other projects, but for this one, it was not difficult to get a data sharing agreement in place and get the data. Even with LiDAR, there's a lot of different qualities and types and accuracies with it. It's not one standard product. So you never know exactly what you're going to get until you get into that agreement.
Yeah. Here's another question about LiDAR. Was the LiDAR data collected at the same time of year as the drone field work? And if not at the same time, what adjustments were made?
So the LiDAR was obtained in 2018 as a custom flight for other purposes. I don't actually know the original reason of why it was done. I don't know the date offhand of when it was flown, but I want to say it was July-ish. No adjustments were made. I really just used the bare earth hillshade product for the mapping. So it's a static thing. It's not something you can really change. It's basically elevation points. And then LiDAR isn't something you normally adjust. You just modify how it looks or how you can use it, because it really is a accurate measurement of height that can be classified to show different types of vegetation, bare earth, water, etc. So you don't normally modify it or calibrate it that I'm aware of. It's more just interpretation and use and modeling. But I'm not a LiDAR expert by any means. And it's also, as I said before, it's incredibly computer intensive. So if you ask for the raw LiDAR data in one map tile, which could only be a kilometer across or something, you literally can get millions or tens of millions or even hundreds of millions of data points. So you can be able to view it and work in it. You can only do it at a really, really large scale of like 1 to 1,000, 1 to 2,000. Because if you try to zoom out and use it on a larger area, it's just way too much for the computer to handle. So that's why these things like the hillshade and other interpretations or models are most often used, because it's a way to use it more consistently, and more importantly, it doesn't kill your computer.
Okay, let's see, one last question. If anybody has further questions, please put them in the Q&A box. So I think you spoke to this, Ryan, but if you could just repeat, how will this information be shared or be available?
I don't have the answer for that. So this was done for the Columbia Wetlands Stewardship Partners with the various granting agencies. So it's their product to use and distribute as they will. I would make the very likely assumption that it will not be an issue whatsoever for them to share it, but that's not my decision to make.
Yeah, and now within the larger project of Kootenay Connect that this one is nested in, we are talking about future data sharing options, and this would be included in that in the next couple of years. But yeah, this is all still a work in progress. Well, Ryan, it's interesting. We've got, I think, one more question about cottonwoods, and then we'll let you off the hook, because when you finish early, you get more questions. So you've done a great job fielding so far, but one more. So looking at cottonwood ecosystem mapping for species at risk along the North Thompson River. So this is very interesting to hear about, and just wanted to say thank you for presenting this. And I hope the project will be shared as well. So not a question, but a statement. So thanks, Shireen. Okay, well, I think that concludes our webinar. Thank you all very much for attending, and especially thank you, Ryan, for a great presentation and all the questions that you fielded so well. And this concludes, as I said, our webinar series for 2021. Thanks to everyone who's participated in several of them with us on our journey. It's been a great series of topics that we've had. And again, you will receive a follow-up email with a webinar link and also a post-webinar survey with just a few questions. If you could please answer them, that always helps us plan for our series next year. So thanks again for joining us, and enjoy the rest of your day.